On our last section of acids and bases, we're going to be discussing buffers. You can think of a buffer as a shock absorber. Something that absorbs the either additional hydrogen or additional OH in a solution to make the pH stabilize. For instance, in this solution, it's just pure water. If we add acid to it, the pH goes down, meaning it's becoming more acidic. Whereas if we add OH, the pH goes up, meaning it's more basic. Remember, with the pH scale, 7 is neutral, from 0 to 7 is acidic, and above 7 is basic. If we have a buffered solution, when we add acid, it starts off at 7, but it only goes to 6.9. It's acidic, but not nearly as much as when there wasn't a buffer. And again, if we add OH, it goes up to 7.1 rather than all the way up to 10.5. So when you're adding an acid or a base to water, the range varies quite dramatically when you add an acid or a base. However, if you have a buffered solution, the range is much smaller. So, what buffers do is they resist the change in pH, and we're going to explain how that happens. We have several different buffers in our body to make sure that our pH remains close to 7.4. If it doesn't, you're going to have issues with metabolism and with the cellular productions and the oxygen being able to be absorbed into the cells. Things along those lines. There's a lot of biological issues that could happen if you don't have a buffer. So, we're going to explain just generally what a buffer does. Remember, A just means acid. It could be anything. It's any generic compound. The H in front of it is that hydrogen that's given off. Whereas here, there is no hydrogen. They have the Na there. So that's actually Na plus and A minus. This is the acid-base conjugate pair. So this is the initial acid, and this is the conjugate base. Meaning it's the acid without the hydrogen there to begin with. We're going to put both of those into a solution. So if we add water here, we have now hydrogen plus rolling around and A minus, the conjugate base, rolling around. But we're also at the same time going to add the A minus to it. So then that hydrogen from the water gets absorbed and we're back right here again. So we're adding both of these to a solution at the same time. What that does is it gives the ability of when we add either an acid or a base to the solution, the impact is absorbed. For instance, if we add HCl to a solution, that breaks up into H plus and Cl minus. The Cl doesn't really do much as far as the acidity is concerned. However, this H plus, when we add hydrochloric acid to it, could cause a huge effect in the acidity. It can make it a much more acidic program. However, when we add H plus, we already have these OH minus floating around from the conjugate base sitting there. Well, that means that this H plus and OH minus are going to come together to form water. So it neutralizes each other and so absorbs some of the impact of the HCl. Similarly, if we add NaOH to the system, we have Na plus and OH minus. Once again, the Na plus doesn't really do much on its own. However, this OH minus can make something extremely basic. But with this HA in the solution, with this acid in the solution, it's going to absorb the impact with that hydrogen, and that's going to come together for water. So essentially what you have here is an acid-base conjugate pair that can absorb the impact of something else being added to it because of the products being an H plus and OH minus. These have to be weak. If they're not weak, it's going to overpower it too much. However, if you have a weak one in there, it has just enough to neutralize it. So in a buffer solution, it contains a weak acid and a salt of its conjugate base. Salt just means that it has some kind of ionic compound that contains that weak acid without the hydrogen. So it could be Ka, it could be Na, whatever. It has to have -1 hydrogen and a metal ion in its place. Typically equal concentrations of the weak acid and its salt. So that way one is not being overpowered by the other. So if we're looking at, for instance, acetic acid and sodium acetate, notice here's the hydrogen and it's being replaced by the sodium. So we have an acid and its conjugate pair, conjugate base. So when this conjugate base is put into water, here's the conjugate base and here's the salt. It just floats around in the water. And then once again, here's our acid floating around in water. There's the conjugate base. So we have a large amount of the acid and the conjugate base both in the solution. So then it can actually absorb the impact if we have hydrogen here. It can absorb the impact of the hydrogen if we have an extra OH minus. It can absorb the impact of that because it'll take that hydrogen away. And it ends up neutralizing itself. So remember the rules. It has to be an acid-base conjugate pair. And it has to be weak. So a strong acid, weak base conjugate pair is not going to work. So if we look at HCl and KCl, HCl is a strong acid, so that's not going to work. H2CO3 and NaHCO3, that will work because remember, if you take away one of the hydrogens and replace it with a metal ion, that's an acid-base conjugate pair. H2CO3 is a weak acid, so that's going to work. H3PO4 and NaCl. Well, PO4 and Cl are not conjugate pairs of each other, so that's not going to work. And then we have HCT, acetic acid, and potassium acetate. C2H3O2. Those are the same polyatomic ion, -1 hydrogen, add in an ion, that'll work. So B and D are buffer solutions. Once again, B and D are buffer solutions. Buffers are a complicated topic, so you might have to review this a lot, but the general idea to take away is that it's a weak acid-base conjugate pair, and they absorb the impact of, they lessen the effect on pH when an acid or base is added to a solution.